So now we'll have Patrick Shepard, who will talk about social network software. And so I don't know what social network software is, but we'll find out, and how to augment it. So Patrick, it's all yours.
Hello, everybody. Thank you very much, Dr. Finkel. Let me go ahead and share my screen here. That's a good intro question. Bottom line is, I really didn't want the title to just go on forever and ever. So I had to chop out some of the descriptive capacity. But let me get this shared real quick, and then I'll give everyone the bird's eye view of what we're talking about. Share. There we go. Okay, we got this going. Let me hit my present button here. No matter how used to Zoom I get, it's always a pain trying to move this little window around and get it out of my way.
It's fine. It looks good.
So this is a paper that Isaac and I wrote along with several others. And the general idea is the following, what I'll be presenting here. For the last couple of years, I have been developing a software suite to do opinion change simulations over a social network. Now, it's a more general purpose software than that, but the opinion change purpose is the first one that I've been putting it to. But since it is a general purpose software, it also lends itself quite nicely to epidemic simulations, and you can augment it in any ways that you want to, and it's fairly user-friendly. So what we'll be doing here today, like I said, the bird's eye view, is that I'm going to be doing two things at once. We built our own COVID simulations on top of my software, and in order to do it, we used concepts from both the paper that Isaac just presented, as well as another one. And where Isaac's paper had to do with interactions, who do you interact with, the sort of the physical space of what we're doing, my paper had to do more with self-protection, so wearing a mask or not wearing a mask, that sort of thing. So what I'll be going through here, the first part of our presentation will be describing how the model is set up. And so this is sort of dual purpose, talking about sort of my software, and then also the other paper that Isaac didn't present, because we use a lot of their mechanics for our own model. So just sort of the same information. So I'll be talking about how we actually set up the model, and then going through some of the results that we saw. And a lot of these results, the flavor of them is along the lines of, if this is the case in the network, if our agents, if our people who are interacting obey these rules, then what sort of things can we expect to happen with respect to the epidemic? Okay, so now I'll go through my slide here. So basically, I've got this software. We adapted it to be a COVID simulation. We incorporate ideas from two recent works, one of which we just heard about. We get to see how different parameterizations affect dynamics within this epidemic process. And then we also do a little bit at the very end where we compare simulation results, kind of getting to, whose question was it? Somebody asked the question about sort of toy networks versus realistic networks. So we compare some results between a sort of standard classical network model with one that's more realistic. Okay, so the general idea here, I'm going to blow through these first few slides because it's all very boilerplate. We have to have a social network model, and that is usually done as a graph. And so you have nodes that represent each of your people in the network, and you have edges that represent connections between them. Now, depending on the model, depending on what paper you're reading, the edges can either represent interactions between people or relationships between people. And so in this case, our edges are meant to represent relationships. And also, as Isaac mentioned, we've got this sort of state of our network where each node at every time step during the simulation is in one of several conditions. And so you've got a few different models. You've got the susceptible, infected, susceptible model, where people bounce back and forth between either being infected or not, but there's no immune state at the end of it. And the one from Isaac's paper is the SEIR model, which we talked about. So if you're susceptible and you come into contact with an infected person, then you become exposed. After a certain amount of time of being exposed, you become infected. And then after a certain amount of time of being infected, you become recovered, at which point you can no longer be infected. So those are the conditions that we have in our model as well. Now, we get into the actions that people can take. Now, the paper that I read to incorporate as I mentioned before, deals all with people's individual behavior. So do they decide to self-protect or not? Under which conditions do they decide to self-protect and why? Questions like that. So the actions in our model that our nodes are able to take, or our agents are willing to take, are to either wear a mask or not to wear a mask. Real quick, could somebody tell me, I don't know if you all can see my cursor when I do this. Is that, okay, awesome. So we can either wear a mask or we can not wear a mask. One simplifying assumption that this work makes is that if you're wearing a mask, then you are automatically not eligible to become infected. So these are just some really, really super high quality masks, apparently. Okay, so if we have the option to wear a mask or not, then there's got to be some function that tells us, that makes that decision. And so we've connected the decision to wear a mask or not to this probability function. This comes straight from the other paper. And I'll mention the actual paper itself at the very end. I'll give the bibliographic information for it. But we took the same model that they used and implemented it directly in ours. And so what this probability ends up being is pretty much the, what's the right way to say this? Well, it's called logit learning, is the name that they've given to this here. And so what you do is you take the payoff that you get from wearing a mask, so whatever your benefit is, and you divide that by the total payoff that you could get among all strategies. So you've got the payoff for not wearing a mask plus the payoff for wearing a mask in this case, because there's only two different options. And so you can see that once your benefit of wearing a mask becomes great enough, then that probability goes up and up, and you will eventually wear your mask. And then there's also this extra term in here I won't go into in detail because it's just a constant, but it's this beta that's a rationality factor. And beta is manipulable such that higher values of beta lead to, higher values of beta lead to the agent choosing the action that maximizes their payoff. So it's their rationality. Okay, so we've got these payoff functions. We need to know what those things look like. So since we have a payoff function, that means that there's some cost and some benefit to wearing a mask, and there's some cost and benefit to not wearing a mask. And the payoff functions for each condition are related to four different aspects of the network. So one is neighborhood behaviors. In other words, if I'm stuck in the middle of this network here, part of my choice of behavior is going to depend on my friend's choice of behavior. We have risk perception. So if you hear, the reports about the COVID numbers, you're going to think, oh, that sounds like a lot, I'm really worried, or that doesn't sound like that many, maybe it's not so big a deal in my area, your risk perception. We also have cumulative frustration, which represents the aggregate cost over time of complying with behaviors that are outside of your normal scope of behavior in order to accommodate the COVID situation. And finally, external interventions. And so this is, it's fairly simplistic the way that we have it set up here, but it's just a numerical value that represents things like government mandates or costs to non-compliance. So these are our payoff functions here, but I want to go through each of these pieces to describe how they are calculated and how they function. So the first one is that we have neighborhood behaviors. Now, one of the interesting pieces of the work that we modeled ours off of is that they use two parallel network representations. You have an influence layer and you have a contact layer. So the influence layer is a static graph, and this represents all of our friendships. So the assumption made here is that your friendships will stay the same over time. You're never going to connect to new people in this particular model. But the contact layer represents the people that we actually have physical interactions with. And so at each time step, the edges in this layer will change because you'll interact with different people. So that's the neighborhood behaviors. Now, the next thing that we mentioned was risk perception. To account for risk perception, we have three different functions to represent sort of three different styles of thinking of our agents. So over here on the left, we have a basic function to represent people who are very sensitive to risk. So people for whom a small increase in the number of COVID cases, say disproportionately increases their, what's the right way to say this without being bristly? I want to say increase their worry over, increase their sensitivity to going outside. If you're highly risk sensitive, then even maybe a small increase would be enough to get you to behave differently than you would have before. We have a second function to represent people who are relatively insensitive to risk. So even if there are rising numbers, they still go out to do their business. And then finally, since we have sensitive and insensitive, there has to be one in the middle. And because I'm a sucker for a corny joke, I had to say that this function is just right. But since this is science, I have to put in a disclaimer that says it's not just right. That really depends on the context of the experiment. But I had to get the Goldilocks in there anyway. So we've got these three different risk functions that represent people of different levels of, say, carefulness. Okay, next we have cumulative frustration. And you may recognize the form of this equation, especially if you've done any Q-learning or things of that nature. But oh, there goes Goldilocks again. But this function here has several pieces to it, but it's fairly simple. So we have a piece of this function, C, and that's our immediate cost, just a one-time step cost of complying with, say, wearing a mask. And then this chunk over here just says, go back through all of the previous time steps and see which ones of them you were wearing a mask for. And then we'll multiply each of those times by a discount factor. So we've just got, or I'm sorry, each of those costs at each of those steps by a discount factor and add them all up. So this is our discounted aggregate cost over time of having complied with our behaviors that we need to. Okay, and then finally we have these external interventions. So like I said before, this represents measures such as mask mandates or things like that, external costs that are imposed on us for non-compliance. And in this factor, higher values just mean stricter measures. Okay, so that was the introduction not only to how we've built our model, but also how the model from the other paper was built. So dual purpose. Now we get into the part where we've modified the other models a little bit. So in both Isaac's paper and mine, there was the situation where interactions with people were indistinguishable from one another. So Dr. Goldsmith mentioned that you might have different types of interactions, say if you're just walking past a person on the street versus if you're in the room with them for 20 minutes. And in our case, we didn't make that particular distinction, but we did say, well, there's a difference between social interactions and business interactions. So there are some interactions that you could undertake, like going to see a friend and hanging out. And as fun as that is, and necessary on maybe a self-actualization level, there are other things that we have to do that are much more pressingly necessary, like going to the store for medicine or getting gas or buying food. And so we don't have as much choice over whether or not we get to partake in those interactions as we do over our social interactions. And so we split both our risk perception and our action choice, I should say, and our interaction choice into two groups. So for risk perception, each agent is going to have some perception of the prevalence of the disease just within their own local neighborhood. So just among the people that they personally know. And then separately, they'll also have a perception of the prevalence of the disease within the overall network. And then when we get into actions, who we want to interact with, well, we have a set of actions that we can undertake, or put it this way, we have a number of actions that we can undertake, and we can determine to take as many of those actions up to that maximum number or none of them. You know, we can decide how many interactions we want to do, and we can decide with whom the interactions take place. So say that we have 5 actions available to us. We're an agent in this network. We have 5 actions. I might say, well, in my own personal neighborhood, there's 3 cases of COVID. So I'm going to eliminate all of my social interactions for the day, but I still have to go get gas and food. So I'll dedicate my interactions to my have-tos rather than ones with my social group. Okay, and being that we've got these separate representations of a local environment versus a global environment, we also added in weights for each of these things. So for each of our agents, you can determine how much each agent, what's the right way to say this? How much importance each agent gives to the condition in their local neighborhood versus that in their in the network as a whole. Okay, so our simulation steps in our approach go something like this. For each step, we iterate through all of our agents. And for each of them, we've got a few actions that we have to take. So first of all, the agents have to decide whether or not they're going to wear their masks. We saw the functions that determine what payoff they get for wearing or not wearing a mask, and we saw the probability of wearing a mask here. So we just go through each of our agents and decide if they're going to wear a mask or not, and then they go ahead and adopt that condition, whatever they wanted to do. The next step is that each agent goes through and determines how many actions they're going to take and with whom. So if they decide to take interactions with their social group, then they'll be interacting only with nodes to whom they have an edge. But interactions that take place on a business basis, so running errands, can happen with any other node in the network, whether or not the two are connected in the influence layer. And so nodes go through, they decide how many actions they want to take, who they want to take them with, and they go ahead and do it. Which leads us into the transmission part. So when we're doing these interactions, when two agents interact with each other, that's when the chance of becoming infected hits. And so in the next phase, we see who interacted with each other, and we calculate who has become exposed or who has become recovered in this past time step. Oh, I'm sorry, I guess that I kind of just subsumed that last module there, but that's what happens. So we go through, we decide if we want to protect, we choose who we want to interact with, and then we actually interact and we update our state. So that's how each step of our simulations go. And now we're down to the results. So a lot of these results I mentioned at the beginning are along the lines of, given these conditions or these patterns of behavior within the network, here are some results that we can expect to see. Excuse me. Let me grab a drink real quick. Now that we're doing everything over Zoom, I'm not used to talking for so long at the same time anymore. All right. So first we'll look at a little bit of the effects of risk sensitivity. So risk insensitive agents, whenever we used this function here as our risk perception, led to a situation where there was very low cost in terms of official intervention, government intervention. However, the disease did spike up, and then it maintained sort of an endemic level here. So I just realized I blew past this. I should describe what we're seeing on these graphs. So the red line here shows the percentage of the network that's infected over time. The x-axis is time here. And then you see the background of our plot goes from lighter to darker blue. So our vertical bands across this plot here, the darker they are, the darker they are, the higher the percentage of people wearing masks at that time step. And so you can see whenever the bands get darker, typically the line tends to go down because people have gotten more worried about the disease, more people are wearing their masks, and so fewer people become infected. Now, when we move over to the middling risk category, we see a very different behavior. So these people over here, they're not very risk sensitive, and so you can see there was never a time when like most of the network was wearing masks all at the same time. But in this case, when people are more sensitive to risk, we ended up with a very different pattern of behaviors here. So the disease would start to spike, and once it reaches some level, then almost everyone in the network, you can see by the dark blue bands, decides to wear their mask, and we push the prevalence of the disease back down. However, once the prevalence of the disease goes down enough, everybody says, well, looks like we're in the clear, takes off the mask, and so you get these light bands leading to another spike. And so you get this oscillating situation in which the disease never actually goes away. Those were a few results having to do with risk perception. Now we also have external interventions here. So we did a series of different experiments to test out different conditions. And one of those conditions was differing strategies for external intervention. So, I have a chat. My chat window's not coming up. If you don't mind, I'll check it in just a second as soon as I can get the chat to come up. So we have three different strategies that we're looking at here. We have a lenient intervention strategy, a graduated strategy, and a stern strategy. So the lenient strategy means that in general, the government is going to be fairly hands-off. They're going to set just one threshold, and they're going to say that if the disease prevalence reaches that threshold, then they will impose on us some cost. But the cost is not necessarily all that high, but it's just sort of a one-off thing. If we reach this percentage, then there's a cost. If we drop below that percentage, cost goes away. The graduated scale says that the magnitude of the cost imposed on us is going to be proportional to the prevalence of the disease. So the more disease there is within the network, the higher the cost imposed to try to get rid of it. Excuse me. And then finally, we have a Stern pattern here. And what this is the strategy in which once we reach some threshold prevalence of the disease, then there's going to be a massive cost imposed on the network. And so you can see some of the different patterns that come up under these different general strategies. So under the lenient strategy, it appears that the disease itself is more prevalent by quite a bit than in most cases, which you can imagine. If there's very little disincentive from adopting a certain behavior like wearing a mask, then not many people are going to do it because there's not a great deal of reason to do so. But when we do hit massive spikes, then everybody is able to come together, at least for a short while, to take care of the situation. Now, the graduated strategy seems to have worked the most poorly of all of the different strategies, because people's incentive to behave in a certain way is proportional to how bad things get. And so if we have the disease, say, on the run, and it's dropping down like this, then that leads everyone to experience a lower cost and therefore have lower incentive to self-protect. And then finally, we have our Stern strategy here, which is basically, you can imagine it as once we reach a threshold of the disease, there is a massive lockdown, and that lockdown stays on for a while. But there's no in between. There's no graduated, there's no suggestions on the way there. It's just if the disease gets to this point, then we're going to impose a massive cost. And so you can see that each of these different strategies has its benefits and its detriments, and they produce very different characteristic patterns of the disease's behavior. Where do we go next here? Oh.
Well, we can point out right now what the chat said, which is look at the scales of these graphs.
Yeah.
You say the middle one is perhaps not very good, but if you look at the scale, it's generally better than the lenient one. And it's generally about the same as the Stern one until the disease goes away. And in your previous picture as well, the scales are very different.
Yes.
And you can see that the risk-sensitive ones do much, much better in general if you put them on the same scale.
Right. Yes, that's true. Now, one thing here, so I will mention, I'll go ahead and mention this, but I was saving it for the end. All of these experiments were done on classic small world model graphs. And when we run the exact same conditions on networks that were generated using a more realistic approach, we do get somewhat different results here. And so I'll just say that some of these, the pattern is more important than the absolute numbers, because, you know, some of it comes down to the modeling, and there's only so close of an analogy you can draw. But I do want to point out, though, since you mentioned that in this case, say the graduated versus the Stern approach, they both work better than the lenient approach. But the color of the lines here, you can also see that as a proxy for how much it's costing the government to impose this intervention. So if the government wants to actually impose something on us, then that's going to have a monetary cost and a labor cost. And so if they have to keep coming in and just dumping money at this thing when it keeps spiking up, that's maybe a less preferable outcome than, say, in the Stern approach, where there's only just a few great big whacks and then it's gone, theoretically, if that is the way that it works out. Okay, and so and also at the end of Isaac's presentation, we mentioned that there's something of a diminishing returns effect that can happen depending on your intervention strategy. And we also saw a little bit of that with this approach. And so this is just sort of a characteristic case that I've pointed out here. And the black line represents the prevalence of the disease in a network where all of our agents are just working on the basic model. So we're not looking at local versus global risk perception or local versus global interactions. Everybody just has a simplified version of the information. And then the red and blue lines, the red line represents when our agents are taking into account the augmented version of the risk perception. And so their friends being infected with the disease has a bigger effect over them, or has an individual effect over them separate from the prevalence of the disease in the entire network. And then on top of that, the blue line here represents agents who not only have that, but we're also differentiating between the different contacts that they wanted to make. So either within their local neighborhood or just globally for business reasons. I saw that I had another chat there. I don't know why I can't see my chat box. I am not sure, but this is like the, yeah, this is the last slide right here. So I mentioned the topologies here. These, don't take too much information from these plots, but just to show, if we let these simulations run out on sort of classical models, you have small world models and scale-free models and random models, so different ways of making your edges in your graph, we can have very different results than if we use a more realistic network generative model. And so over here, you just see the disease prevalence and the mask prevalence over time on a typical small world network. Whereas over here, I used a different network generator that was actually developed by Emery Huffbauer and Nathaniel, who's in our meeting with us. And I could not give your network generator justice if I tried to describe it. So if you want to break in for a second, Nathaniel, and just give a quick sentence about how that network generator works instead of, say, a small world one, you're welcome to.
Sure. So essentially, in a very kind of SparkNotes explanation of how our model works for generating social network topologies, we essentially consider a proximity space where we consider some arbitrary number of dimensions. And these dimensions can represent race, socioeconomic status, and a whole slew of different social parameters that people can be represented by. And based on the distance between people in these proximity space, we have edges that are being established. And our model demonstrates a lot of the topological features of real world online social networks and social networks in general. So,
thank you, I appreciate that. So we didn't dig as far into this as we wanted to. The deadline came looming, so this is more in the works here. But it does stand to reason, though, that some of the conclusions we may draw from more classical social network modeling approaches may be limited in their informational capacity with respect to newer, more realistic network generative models. And was that it? And then we have our bibliography. So in case you're wondering about the papers, this is Isaac's paper, this is the other paper that we used, and this is the paper describing that network generator model. And if we want to, I don't know if we want to, but I also have the software pulled up so we could watch we could watch a little simulation or two if you wanted to.
How big were your networks?
So our networks were 1,000, with the exception of that other network generator model network that was significantly larger. It was pre-made. But the proportions were all the same. So I didn't mention the structure of the networks. In this second paper here, the Yay paper, they had particular parameters that they used to generate their networks. They used small world, and they had a particular number of edges, they had a particular number that was the average number of connections for each of our nodes. And so I just stuck with their structure on that. I think I got lost in the woods of answering that question. I forgot what the question was exactly. Oh, the size of the networks, right? So they were all 1,000 in our work.
A question from the chat: are the underlying networks static or dynamic?
So that goes back to that influence layer versus contact layer thing that we mentioned before. Here we go. Okay, so the influence layer is static, and this is the one that shows us what our friends are doing. So, payoff functions. I think that I did forget to mention this one piece. Oh no, I need to come back here. The payoff functions. Right, so this summation at the beginning of each of these payoff functions is sort of a homophily term. It's just what percentage of my friends in the influence layer are doing the same behavior that I am. So if I'm wearing a mask, what percentage of my friends are wearing masks, and vice versa. Now the contact layer is It does not depend on the influence layer, and this is the one that determines the interactions. So when I actually go out to interact with people, I may not necessarily interact only with people that I have edges to in the influence layer. They may be outside of my personal neighborhood. Did that answer the question properly?
So how do you set up those dynamics? How do you determine with whom you interact?
So the way that it works mechanistically is the interactions in this network, they use something called an activity-driven network that I just learned about in doing this work. And so what it says is that each node in the network is assigned some number, some real number between 0 and 1. And at each step, we just do a random number. And with that probability, that number between 0 and 1, that node will take a set number of actions. So in their work, that set number of actions was 13. They used the COVID literature to determine that number, but it was 13. So I used 13 as well. And in our work, what happens is each node, if it is activated, so if it's told that it gets to take its 13 actions, then it says, well, I have a maximum of 13 actions. I can restrict that if I want to. So if I'm looking around and it's too risky outside, I might restrict that. I only want to take 8 actions. Once you've determined how many actions you want to take, then you split those between your local neighborhood and your business interactions that you have to do. So you might say, well, I want 60 of those 10 interactions that I'm going to, I'm sorry, 60% of those 10 interactions that I'm going to take to be with my friends. Now, those are people exclusively that I'm connected to in the influence layer. And the remainder of those actions, I'm going to take as business errands, in which case it's just randomly chosen. Random nodes throughout the network are the ones they interact with.
So it's a very much more complicated model than we've seen in the first paper. But we're going to have to call a halt then to further questions. I'm sure that Patrick will be available for further questions, and Isaac as well. And so I want to thank both of you for quite an interesting show of how epidemiology can be modeled. Right. And stay tuned. We'll meet again, talk about the EDUCE project, I believe, next week. See you then.